Welcome back to I Can Science That. Let's continue our discussion of work. What exactly is work and how does that relate to the concept of momentum? We found this definition for work, and let's talk now a little bit about why it should be that and maybe whether we should consider something different. So, work. What does it mean to do work? Let's imagine our job is to move a crate to the other side of the cargo bay.
Really? There are Klingons on the other side of the hull, and this is our job? You son of a...
Moving a crate, what does that take? It's going to take force. We're going to have to push on the crate. And if we push really hard, is that doing work? Or does it only count if we're able to move the crate? What if it's a really heavy crate and I push on it and it doesn't move, right? If it doesn't move at all, I'm still working hard. I'm still working up a sweat here. Am I doing any work? Even if I push 10 times as hard, if I'm not able to get the crate to move, I think the foreman is going to say that I didn't get the job done. Right? That's not getting the job done. And even though I'm sweating up a storm, if the object is not moving, I'm not actually accomplishing any work. So the job is to move the crate. I have to move the crate to do some work. I think that's a reasonable perspective. So no matter how hard you push, if you didn't move the crate, you did not do work. And that means force cannot be work. We cannot say that force is work because you could push really hard on something and have it not move, right? And if it doesn't move, we didn't accomplish anything. That can't be work. Let's take a look at this sliding friction example where we have matching masses, but we launch them with different speeds. And what we had said is that the yellow object goes 4 times as far as the blue object. That was the experiment we've kind of been talking about. In this context of doing work by moving an object, I think we ought to agree that if our job was to move the object 4 meters, in the case of the blue object, we have not done the job. How much of the job have we done? Have we done half the job? I think it's pretty clear we have not. If we want to move the blue object to the 4 meters that the yellow object has gone, we're going to have to do it 3 more times. We've only done 1/4 of the total job. And so by that logic, 4 times the distance is 4 times the work. So maybe distance is the work. Maybe that's what it's all about, right? If all my job is to move this crate from one spot to another, then maybe how hard I work has nothing to do with it. It's just about the distance.
Don't worry about it. Get to work. These crates aren't going to stack themselves.
Let's consider, what if I want to move these 3 blocks, my 4 meters? If I just do one of them, then I've done 1/3 of the total job. I can do it 2 more times to get the job done. This is the equivalent of moving a 1 kilogram block over 3 times the distance, right? I've done 3 times the job by going 3 times the distance. I just did it on 3 separate objects. Consider instead, let's combine it into one big object. So we're going to do one big object, and the job now is to move that object over my 4 meters of distance. Wouldn't that be fair to say that that's the same amount of work as if I had moved it as 3 individual blocks? How much work was that, right? Let's say, how much work was it? In our previous example, we had worked out that we were looking at 1/2 Newton of force from friction in that example. So let's stick with that. And friction is a topic we really haven't delved into. I'm not planning to delve into it in this video, Maybe in a future video we can talk more about it. But the simple version is to say that if we were seeing half a newton of friction from the block, then pushing with anything less than half a newton will simply not move it. The friction will stop the block. If I can't push with half a newton, I can't move the thing. So I'm going to be trying to push with the minimum possible force to get the block to go across to the other side. And maybe we'll talk about friction in some future video. If anybody's interested, give me a shout. Maybe we'll go there. For now, I'm going to apply my half a newton until I get the block to the other side of the room, and then I'm going to stop pushing. And friction will bring the object to a stop. Okay, sweet. So let's do it again with our 3-block combo. I'm going to do 3 at a time. If it took half a newton to move 1 block, again, without going into how friction works, the way we model friction, it's going to take 3 times as much force to move a stack of 3 blocks. And I think that's pretty reasonable to expect. So let's compare what would be the difference between moving individual blocks across the room or moving this stack of 3. If we did the blocks as individuals, each block took us half a newton to move it, and we pushed for 4 meters. But we did it 3 total times. And if we multiply that out, we get 6 newton meters of work done. If we push the stack of blocks all at once, we said it took 3 times as much force, but we only had to move it over 4 meters. But again, you'll notice that's the exact 6 newton meters of work. So what have we decided? I think we've decided that based on this context of what it means to accomplish work, how hard we push on the object is part of the answer. And the other part of the answer is how far we manage to make it move. How about if I pushed the object even harder? If I pushed the object harder, I could get that thing going faster. I could move it across the room much quicker. Would that count as more work? I think we could make the case that that's certainly seems like more effort, but we didn't get any more work done. We just got the work done faster. And as valuable as that might be, that's not more work. It's just faster work. And based on that statement, I think it's fair to say that we should not be including time as part of our work formula. The work formula is going to come from the amount of force that we applied, and it's also going to come from how far we moved the object. So that brings us to this. Work is just force times distance. In our formal equation that we started with, we also had an extra term on there with the cosine of theta. So what is that about? That little cosine theta there is a nod, if you will, to the idea that not all of the force that we used was actually accomplishing anything, right? Maybe some of the force was sort of wasted in our efforts. Like if you push on something really hard and it does not move at all, you're not accomplishing any work. That's in here with this distance. But what if I apply a force and kind of like an angle? I'm like pushing the crate kind of down while I'm also pushing it. Then I'm going to do extra force. I'm going to put in extra effort. But that extra force doesn't contribute to the job that I'm accomplishing it. So this force here that we're saying is the force that sort of causes the movement. This is the amount of the force that's contributing to the movement of the object. So that's the physics definition of the word work, and what I hope is a pretty good intuitive explanation of what it means and why it is the way it is, and why we don't just use momentum as work. But let's consider momentum. momentum and the conservation of momentum seems to be pretty fundamental to the universe that we live in. I think we can agree that momentum is conserved. Perhaps we can agree that momentum is conserved in all cases. Certainly, what we normally would say is that momentum is observed in a closed system in which no net force is acting. What do I mean by that? Another way to say that might be to say that a force, what we call a force, is when momentum is being transferred from one object to another. If momentum is exchanged between objects, the way that exchange is going down is what we call force. Force is a measure of how much the momentum is being exchanged between objects in the system. So what is a net force then? A force acting outside the system is just a force that we're not considering that object. Whereas that object that is providing that momentum is not part of our system. That's not what we're considering. Not what we're talking about right now. Okay. So for example, let's say I'm going to push on the crate and I get the crate going. I push it and it accelerates. In order to do that, I have to apply a net force to it. And that means I'm going to be transferring some momentum to it from outside the system. If I widen my system a little bit, I will see that where I have transferred the momentum from is the ground. I have to push against the ground in order to push with an equal force on the crate. I will transfer momentum into the crate, and the exact amount of momentum must be balanced to keep the conservation of momentum. Where that balance goes is into the ground that I'm pushing on, right? And because the ground I'm pushing on has a tremendous mass, we're not going to see any measurable velocity there. But the rule of conservation of momentum says that it must be there. It's just so small, no one would ever care, right? So what we're going to do is we're going to draw our little system box around just the crate. We're going to ignore this object. We can treat that as a net force. So that means momentum being transferred from just outside the system, just from somewhere else. So when we started off, the block was at zero momentum. It's just sitting there. We get it going, we push it, and then we let it come to a stop. At the end, it's once again at zero momentum. So I have moved the crate across the floor. It started with zero momentum. It ended with zero momentum. In the meanwhile, I borrowed a little bit of momentum maybe from the ground object. I transferred some momentum from the ground object up to push on the crate, and then I gave it right back at the end. So that's also zero net transfer of momentum. There's been no transfer of momentum anywhere, but I moved the crate. I gave it some momentum and then it gave it right back. So we started with zero momentum, we ended with zero momentum. And in between, maybe we drug the crate across the floor and we had to push against friction. To do that, maybe we generated some heat, and maybe the heat is actually momentum in the particles in the ground, and that's how we should be looking at this. Maybe we should not be considering that the work we did was a measurable, meaningful quantity. Let's see if we can use conservation of momentum to investigate these moving blocks, and from that context, can we explain the movement of the blocks purely with momentum? We're going to start with our similar masses. We're going to give them double the velocity. Like the yellow object is going to get double the velocity. And we see that the starting momentum is twice for the yellow object. And we launch it. And of course, it goes 4 times the distance. My understanding is that it's not disputed. That's in the original thought experiment. We saw that twice the momentum did 4 times the work. What about going the other way? Let's consider applying some of this work concept into the blocks and see if we can use that to generate momentum. What if we, instead of just using our springs to just fling these things, let's do some work on the blocks and generate momentum by applying work and see how that comes out. So for this thought experiment, let's drop the friction. Let's just imagine a frictionless surface. So I've changed it to like an icy blue. It's a zero friction surface. We're going to apply a steady, constant force to our block to accelerate the block. In our previous example, we had half a Newton of friction. This time, we're going to be just pushing on the block with half a Newton to accelerate the block along the ice. How fast will it accelerate? Just a little quick math here using the equation F equals ma. We can solve that for the acceleration the block will have. And half Newton applied to a 1 kilogram block should result in half a meter per second every second we're pushing on the block. So if we push on it for 1 second, we should get it up to half a meter per second. If we push it for 2 seconds, that should accelerate the block up to 1 meter per second. Okay, that seems pretty straightforward. In that amount of time, the block is going to cover 1 meter. And I'm not showing the math for that particular piece of the puzzle. If you need to see that, let me know, and I'll show you how we can get that. Okay, so the block is now moved a meter, and we're going to let go. We're going to stop pushing. But the block is not going to stop because it's on that frictionless surface, right? No more friction in this example. So we've left the block at 1 meter per second. And that is the equivalent of 1 kilogram meter per second of momentum. And a kilogram meter per second can be called a Newton second. So we've got 1 Newton second of momentum. How much work did we do to get us here? We did half a Newton of force, and we pushed for 1 meter. So that's half a Newton meter of work. Maybe that's just a consistent conversion, right? Maybe just every half Newton meter of work you apply, you get another Newton second of momentum. Let's look at that. Let's consider pushing for twice as long. We're going to do the same exact half a Newton, same exact 1 kilogram. And this time we're going to push for 4 seconds. We're going to push for twice as long. In 4 seconds, we're going to get that brick up to 2 meters per second, twice as fast. Push twice as long, you get twice as fast. In that time, we're going to cover 4 meters. Not 2 meters, but 4. Now, why is that? In the first 2 seconds, we covered 1 meter. But at the end of that time period, the block was already up and going now. It's already going 1 meter per second. So in the next 2 seconds, with the block already off to a good start, we're going to cover distance much more quickly. So we're covering a lot more distance with the second half of the push. When we're done, we will leave the block sliding along on our frictionless surface at 2 meters per second. We did half a Newton times 4 meters, or 2 Newton meters of work. So that's 4 times the work. But we only got twice the momentum. Let's look at this broken down in a little chart here. I've got it broken down a second at a time, and we're going to look at halfway through. At halfway through our little slide, we've been pushing for 2 seconds, and we've built up 1 Newton second of momentum. And then in our second half of the push, we've been pushing for 4 seconds now, and we've built up twice as much, 2 times the momentum, but it's 4 times the work. Now look at this. This is half, and this is 2. So 2 is 4 times the amount of work. And I think there's a case to be made there that only twice the momentum doesn't make sense that we would call that 4 times the work. It doesn't seem reasonable. Why are we squaring that? Why are we squaring the velocity? Ultimately, what's happening is the velocity is being squared there, right? Why is that? It doesn't make sense. This should be what we call a doubling. This is the work we did, not this. This is a nonsense number. But let's consider it again from how much effort we actually had to put in. When we started our push, the object was at rest. You're standing on the ground and you push with half a Newton. As you push, the object starts to accelerate. In our second half, we're still having to generate half a Newton of force, but we have to do it while the crate is moving at 1 meter per second already. That means we have to kind of jog along with the crate while we're pushing. And it just keeps getting worse and worse. As we keep pushing, the crate keeps going faster and faster and faster. So it's not enough simply that we are pushing for 2 seconds per block here. We're pushing for 2 seconds while we're running along with the crate. It's kind of like trying to push against something while you're running on a treadmill. Perhaps that gives you a little bit of an intuitive feel for why it is more work to push on something that is already moving than it would be to push on something that is at a standstill. And that still seems kind of wrong to you. The idea of having to run along with something while you're pushing on it, adding up to extra work, if that doesn't seem intuitive to you, maybe go and look up acceleration curves for cars. Notice that the acceleration curve for a car shows the car can accelerate much more rapidly at a standstill or at a slow speed than it can at a higher speed. And part of that is, of course, from aerodynamic drag, but a major contributor to that effect is the fact that the car is already up and moving, like in this example. The car's already up and going. Applying additional force to it means that that engine has to rev up to match the car's current speed and then continue pushing harder. That's even true for electric cars. Of course, it's true for electric cars, which are even simpler. We won't have to deal with changing gear ratios or anything. Most electric motors in electric cars are capable of generating consistent levels of torque, which is the equivalent to force in this example. And the consistent level of force that the car can put down reduces the rate of acceleration the faster the car goes. And that's because of this exact phenomenon here, that the car is already up and running and has to sort of chase itself down. It has to keep running with itself while it's pushing. And that takes extra effort. Coasting does not take any effort, right? You can just put the car neutral and you can coast, no effort required. But if you want to accelerate, you'll have to apply that force, and that means you're going to have to run along with the object and push on it. Okay, let's take a pin in that one. We'll come back next time and try to explore coming at this from strictly a momentum point of view.